So what we discussed in our last class, among other things, is that the term EMF and voltage, they are practically the same by definition. They both mean energy by charge or work done per charge. Unit is joule per coulomb, which is volt. And the purpose of any EMF source, it can be battery, it can be a generator, it can be a dynamo, it can be a photovoltaic cell. The purpose of any EMF, the purpose of any EMF generator or any electrical energy source is to convert other form of energy into electrical energy. And for those things we use the term EMF, and devices which use electrical energy to convert it into other form of energy, for those devices we use voltage or potential drop, to be more exact. So we talked about these things in our last class, and also that how does the voltage gets distributed as 1 coulomb of charge flows out from the battery. So for today's class, we're going to start directly from the idea of, first of all, the idea of conventional current. We're going to talk about this historical mistake, and then we're going to talk about the idea for how does a circuit actually does its job, and how does current flow through the whole circuit and everything. One of the important thing about electricity is that we human beings as a species, we have known electricity for a very long time. Like, people have known the effect of lightning, and people have known about the idea of having attraction between two objects which are up together. So basically the idea of static electricity of opposite charges attracting each other. People have known these effects for a very long time, long before protons, neutrons, or even the basic structure of atom was discovered. So when scientists were doing their discoveries and doing their and coming up with theories and statements and laws to explain stuff, they needed a way to explain the flow of charge to go from one place to another place. So out of no physical proof, without the presence of any physical proof, out of just guess, scientists of the time assumed that the current is a flow of positive charges that is going from one place to another place. So what they assumed, that if we have, let's say, an object, let me just try to draw a basic battery. Let's say this is a battery of modern world. Let's say this was available back then, and what they assume, that if we connect this thing with a, I'm gonna place a light source over here to provide some resistance within the circuit, because without the resistance this can be pretty bad. I'll talk about it after a while. So what the scientists found out that if we have a circuit like this, or if we have a device like this, current will flow, and this light bulb can glow, and the glow of this light bulb essentially represents that charges are flowing through this circuit, and which is converting the electrical energy delivered from the battery, which is converting into light and heated energy in the bulb. So what they assumed, that current flows from the positive end of the source to the negative end of the source, and the particles which flows are also positively charged. So positively charged particles flow from the positive end to the negative end, attempting to reestablish the balance between the two ends of the battery, and that's how the current flow happens. And this idea persisted for a pretty long time, till any physical evidence or proofs were available to us human beings. Then in 1911, in 1905, Sir Ernest Rutherford, scientist Rutherford, actually proposed his experiment, and Geiger Marsden and some other scientists around the globe, they performed this experiment individually and in groups, and they found out unanimous results, that the structure of atom is like that. The center of the atom is extremely tiny, extremely massive, extremely dense, and highly positively charged. They named it nucleus. And the periphery of the nucleus is basically an empty space within which electrons are existing. And Niels Bohr came along, and he proposed that these electrons are only allowed to exist in predefined shells or predefined energy levels in which they can exist. They cannot exist anywhere in between two shells. They can only jump from one shell to another shell, upwards or downwards, but their existence around the nucleus are in some predefined energy levels or shells. So that's basically how we came to have a complete understanding of what the uh, elementary block of matter or substance, the atom, is like. That's the point where we actually understood that that's how atom is like. That I mean, stacking up one atom after another atom, we basically have the whole universe going on around us. So at that point, scientists got to understand that positively charged particles slash protons are practically stuck at the center of the atom, which is the nucleus, whereas the negatively charged particles or the electrons are going around in the going around in orbits, and the outer shell layer electrons, they can become detached of certain atoms for specific type of materials. For example, metals, they can give up one or two or three outer shell layer electrons pretty easily. For in the periodic table, we get them in group 1, group 2, and group 3 elements. So they find out that some elements can give up their outer shell layer electron pretty easily, and some objects don't. And objects which can give up their electrons, 1 or 2 or 3 electrons pretty easily, they can have a lot of free electrons or delocalized electrons within their whole piece or within their whole structure. And whenever we produce a small bit of potential difference or charge difference, opposite of charge is applied on two sides of that object to recreate the balance. These charge particles slash these electrons basically flows from their saturation location, or from their, or can I say, from their rich location towards their poor location, or from the location where they are too many to the location where they are few. Or the negatively charged particles actually flow from the negative side of the voltage towards the positive side of the voltage to recreate the balance. So it was later understood. I mean, once the whole idea of atom was proven, scientists got to understand that positive charges don't create their current. Actually, the negative charges slash electrons actually produce the current. So then came a singular problem that scientists had to do. One, they had to pick on decision. I mean, what would have been a better thing, or what you can think to have been a better thing, is that they could have defined the actual truth as the new idea, and should have gone with it. And that's what should have done. I mean, every literature or every theory that has earlier was that was done earlier by adopting that the current flow happens from positive to negative side of the battery should be changed, and that's how it should work out. But the scientists, the group of scientists, or the peers, or the group of people who actually were in the decision making position, they decided that no, we are not going to do this correction, because we've been using the current direction in this manner for a very long time. Changing this direction can prove to be very difficult for altering all the theories and altering all the redoing all the paperwork and everything. So they decided that we are going to keep the conventional current in the same way that we have been using it, but we know that the actual current deep at microscopic level is created because of the negative charges or the electrons. But because we have been using the current in this fashion or in this direction for a very long time, we're going to keep it as is. And that's why we're going to call it conventional current. So from that point onwards came the idea that if we whenever we have a circuit, I mean, this is how we uh, prefer to represent the charge flow within a circuit. That if we have a battery, long sides positive charge, and a small size negative charge, and you connect the, hold on just a second, sorry, I had a call from the office, I had to pick it up. Office renovation একটা চলতেছে, so every now and then it happens. So this is how the current duration thing that works. That if we have a battery like that looks like this is a positive and this is a negative, and let's say we connect a device, a bulb. I commonly use a bulb, and not using a switch in this circuit. This is not necessary or not essential for the time being. So this is the complete circuit. The way we prefer to show this right now is that whenever we'll show the current, we'll give an arrow from positive to negative end, and the current, which is usually symbolized by the term I, is gonna flow in this direction. So conventional current slash current of a circuit would generally mean conventional current, and that would be directed from the positive end of the battery towards the negative end of the battery. This is a historical mistake that scientists decided to do, and we've been doing it forever since. One of the implication of this thing is that you need to understand that this doesn't actually make any problem in our calculation or in our concept. This seamlessly or perfectly works for the actual sake of science or equivalent ideas. So even later, whenever we actually could, or I mean years have passed by, why didn't we bother to change the direction of conventional current? Because it is actually a harmless thing. It's a mistake and someone decided to keep on that mistake, and we've been doing it ever since, and it is not a harmful thing. It just doesn't make any difference, because eventually what we'll learn in our AS level, that depending upon the duration considered, or for an unknown value of current within a circuit branch, if the calculation ultimately gives you a positive value for your assumed direction, then the current is actually in that direction. If a calculation gives you a negative value, then the current will be in the opposite direction. The magnitude, however, would always remain the same. This comes from a set of calculation called Kirchhoff's law. So you're gonna learn about these, or some people pronounce his name as Kirchhoff. It's a weird name. It looks like this: Kirchhoff. So Kirchhoff. So anyway, so you're gonna learn about this. So this is actually not a big deal for those who might feel like that this why didn't we bother to change it? We don't actually have to change it. I'm just telling you this in person with so much emphasis so that you do not mess it up. Conventional current is shown on the circuit wire with an arrow with the symbol I, and for going from positive to negative. If we want to ever represent the direction of electron flow within the circuit, we usually prefer to show it with an additional arrow outside the circuit. For example, in this case, the electrons are going to flow from the negative side all the way to the positive side. So we can actually draw the electrons in this manner, or you can draw it anywhere else. That also works. All right. So this is the basic idea. The next thing that I'd like to discuss from this chapter is the idea of continuity. The idea of continuity means, let me just give you a bit of an example. I'm not sure if I have discussed this earlier with you, but I'd like to discuss with you at this point anyway. Let's say we have a battery over here, and we have 3 bulbs. The bulbs can be identical, can be non-identical, doesn't matter. And let's say we have a switch over here. Okay, I'm naming these bulbs A, B, and C. I want all of you to listen here really carefully, because I'm going to ask you a question and I'd like you to answer. When the switch is closed, which of these 3 light bulbs light up first?
A.
Okay, one of your friends, classmates just assume it is A. That's one guess. Yeah, that's a response. Anyone else? Anyone? You're allowed to do mistakes. That's the whole point of a class. So if you have an idea, if you're not sure, it's okay if you are quiet. No big deal. But if you have some idea that is based upon some actual thinking, and you think that there's a reason behind your idea, you are very much welcome to share with us. No one is going to say C, because actually current flow happens because of electrons. Maybe not. Okay, let me help you to understand how does the energy flow happens within a circuit. I want all of you to visualize the circuit any circuit to be to have some characteristics, to look like something very specific. Here's an example. Let's say you have a hollow cylindrical tube of flexible metal. Let's say it's a rubber tube, like a garden pipe or something like that, and you have small marbles which has the exact same diameter as the inside of this tube. And let's say you have a lot of these marbles, like a lot of these marbles you have. I'm not drawing in equal size, but assume they're of all of equal size. If you start to push in marbles through this tube one by one, slowly what's gonna happen? I mean, you're gonna push in one, and if you push in the second one, this is gonna push in the first one. If you push a third one, that's gonna push the first and the second one, and slowly the entire tube is gonna get filled up with marbles. Eventually, there will come a point when the entire tube would be filled up with marbles in such a way that all the marbles would touch each other side by side. It's not actually like my drawing, but the marbles would practically touch each other, and eventually there will be a marble coming up over here, which was your very first marble. That can be achieved, right? Example like বুঝতেছো বলমান? Is it making sense? It's a hollow rubber tube, and you have some marbles with the exact diameter of the inside diameter of the tube, and you're pushing in the marbles one by one. Now comes the idea. When the entire entire tube is filled up with marbles, if we then push one more marble on this side, you're gonna have one marble coming out on this side. Every single marble that you're gonna push on through this side, one marble is gonna come out over here. And this number will never change. If you push in 10 marbles, you're gonna have 10 marbles coming out. This is exactly how a circuit works. All of you guys need to understand. When the switch is open, let me just draw the switch open. When the switch is open, this circuit, at any part of the circuit, I mean, we cannot say this circuit is practically charged anywhere, because you need to understand the state of charged means there is an overall imbalance within the number between the number of electrons and protons. You need to understand that this circuit all over is practically neutral everywhere. You might wonder that how does a battery can be neutral? I mean, battery produces positive and negative charges. This is exactly what is important. Try to understand. If I try to represent the battery like a rectangular block, and let's say this is supposed to be one of our plate, and this is supposed to be a negative plate, this is supposed to be a positive plate. The way the chemical reaction happens within a battery is that if it sends 100 electron over here, it would have taken 100 electrons from this plate. So this one has lost 100 electrons, and these 100 electrons have come over here. But altogether, the total number of protons and electrons within this battery is practically the same. The chemical reaction did one job. It took the electrons from the positive end of the battery and placed them on the negative end of the battery. But the total number of protons and electrons within the battery is very much the same. So if you are ever asked the question, a battery is a neutral object, is it true or not? The answer is a solid yes, it is true. But because of the chemical reaction, there is a separation of positive and negative charges, and that separation is equal on both sides. Any battery will never become actually charged. I mean, you cannot drain anything out of a battery, or you cannot push in electrons within a battery if you only provide one watt. Try to think about it. Let's say if you have a battery that looks like this. Let's say let me just draw a battery circuit symbol. This is a battery. If we take one end of the battery and connect it to the ground, will you think that there will be some current flow within this battery? Will this battery drain just because I'm connecting it with the electron side? What do you think? You can say yes or no.
No.
Okay, no is the response. Anyone else?
No.
No, this battery will not drain. And you can also seen it with for other cases as well. I mean, if I just even I mean, this is pretty simple. I mean, if you have an open circuit, let's say you have a battery and you have a light bulb that you do not want to disconnect with the other end. If you just provide it in a connection like this and not connect with the positive end, this light bulb will not glow because current flow will not happen. The reason current flow will not happen is because the battery will always work in such a way that it will always give up and accept equal number of electrons. If you take out 100 electrons out of the negative end, you have to deliver 100 electrons on the positive end. The total number of the electrons within the battery will always remain the same. It will give away and take in equal number of electrons. The only thing that it does is that when the electrons come out, they have bigger amount of electrical energy compared to the electrons that it accepts over here. So it accepts low energetic electrons and it gives out high energetic electrons. So all that it does is simply make the electrons more energized so that those electrons can travel through the circuit, go to the relevant components like light bulbs, fans, TV, fridge, computer, mobile cell phone charger, you name it. So it can go to all the electrical appliances that you want, and eventually it can give their electrical energy to those devices and eventually come back to the source drained. That's the basic purpose of a battery. It will always give out an acyclical number of electrons. The same example that I was trying to give you over here is this thing. The circuit, any circuit, is pretty much like a tube that is filled up with marbles all the way in. The moment we'll close the switch, electrons are gonna flow. Electrons are gonna have a closed path to flow by. Try to think about it. Whenever electrons will start to flow, let's say if this end of the battery gives out, let's say 10 electrons within a duration of, let's say, hypothetical 1 second. This is not, these numbers are not logical, but I'm just trying to make sense with you. It is essential that within that same 1 second of duration, the positive end of the battery must have also accepted 10 electrons. This essentially means that 10 electrons have flown through the whole circuit. Now, you have to understand that this 10 electrons flowing through the whole circuit doesn't necessarily mean that the 10 electrons which went out of the negative end have made their journey all through this wire and eventually came back over here. These are not the exact same electrons. This is not like the journey of the hobbits. 10 electrons get out of the negative end, they push in like the marbles of the tube, and 10 electrons get entered over here. So this basically like what can I say, like the assembly of your school, like in a single file. Does the idea make sense? Current flow
Yes,
within
sir.
a circuit happens in this way. This is why whenever the switch is closed, now the bulbs is going to start glowing first. All of the three bulbs, each of the three bulbs will glow simultaneously. And if you switch it off, all of them three will go out simultaneously as well. None of them will glow up first, none of them will glow up last. Now, interestingly about what happens for their brightness, that's a different issue. The brightness, I'm going to talk about the electrical power thing after a while, and the brightness will be a part of that discussion. I'm just trying to tell you that which one will glow up first and which one will glow up later. The answer is none. If the circuit is closed, all three of them will glow up at the same time. If the circuit is open, all of them will go out at the same time. Now, uh, you might wonder that, well, when the switch, I mean, or you might not wonder. Let me just tell you what I'm trying to tell. Uh, when the circuit is open, when the circuit is open, how does how is it possible that every part of the circuit has energy? For example, here's the deal. I told you about voltmeter in the earlier class when I was discussing about the part of the voltage drop. Let's say if this battery has a voltage of, let's say, 12 volt, it means this 12 volt will be distributed across all the series components over here. I haven't talked to you about series or parallel combinations yet, which I'm gonna do in a while. This is basically a series combination. Just hear me out for the time being. And in this series combination, voltage will be distributed. Which it simply means that whenever 1 coulomb charge will be coming out from any end of the battery, you can consider positive charge coming out, hypothetical positive charge leaving from the positive side for conventional current. You can assume actual or realistically 1 coulomb of electrons coming out of the negative side. Either case, 12 joule means 12 joule 12 volt means 12 joule per coulomb, which means 1 coulomb of charge is going to have 12 joule into it. And this charge is going to start their journey from one of the end of the battery. And over the process, they're going to spend their entire 12 joule of energy, or they'll convert their 12 joule of electrical energy to other form. And eventually, whenever they'll be received back into the battery, they'll have zero electrical energy left. That's the basic idea of 12 volt. Now, if you wonder that how is it possible that all the electrons which are practically all stationary, the moment we close the switch, they all start to flow and give energy to all of these bulbs individually. I mean, does it essentially mean that whenever we will close the switch, immediately these electrons and all the electrons over here, they all started to have energy? The answer is a solid yes. The idea is very simple. I'm gonna show you. I'm gonna show you this whole thing with a little bit of what is it called, voltmeter as well. Just let me take out this circuit a bit out. I don't have much space here. Okay, this one should do. Do you guys remember that what I told you about the voltmeter the other day? That what does a voltmeter do? Anyone? What does
Measures voltage across 2 points in a circuit.
precisely? Question. Thank you. For those of you who don't remember, a voltmeter measures the voltage across 2 points of a circuit. It basically measures that what is the difference in energy for each coulomb of charge across 2 points of a circuit. And I told you that if you don't have a device, or if you don't have a draining device or electrical component between 2 points of a circuit, then that is not going to measure any voltage difference. Now, here's the important bit. Try to understand. I'm gonna show you this information part by part. Let's say we have some voltmeter connected over here. Oops. Should I tell you the voltmeter connection right now, or should I go for Ohm's law? I think I can go for Ohm's law, and then I can get back to this figure once again, because that will make better sense. Yes, that will make better sense. Okay, I'm gonna show you a bit more of this circuit after a while. But before I go do that, I'd like to talk to you about Ohm's law. Ohm's law was the topic from which we had to actually went in the definition part, because to explain Ohm's law properly, you have to understand what is voltage and what is current, because and also what is resistance. So we have covered all of those definitions in our last class and including today's class as well. So the Ohm's law tells us this thing: at constant temperature, the current flowing through at constant temperature, the current flowing through any conductor is directly proportional to the voltage slash PD applied across it. One of the very important thing that the students in many cases forget to write in the statement of Ohm's law is this part. This is the precondition for Ohm's law. This is really important. This is a precondition for Ohm's law at constant temperature. You have to mention this. If this logic is not fulfilled, Ohm's law is not applicable. There is one of these precondition that you have learned in one of your chapters in Newton mechanics as well, which is Hooke's law. Hooke's law tells you what? Hooke's law tells you within the limit of proportionality, the applied force is directly proportional to the extension. So it is only applicable within the limit of proportionality. Beyond that point, it's not applicable anymore. So similarly, Ohm's law tells us that at constant temperature this happens. So if I just try to write this whole thing in some sort of circuit, let's say we have a conductor over here. Just to make sense of the conductor, I'm just trying to show you some resistor over here. Let's say the resistance over here is R, and using a battery, we're going to apply some voltage across it. So let's say this source of or battery has a voltage of I across it, and the conventional current that flows to the circuit is I. What the formula tells us, or what the law tells us, that at constant temperature, the current flowing through any conductor is directly proportional to the voltage or PD across it. So it essentially tells us that I is directly proportional to V. This is the expression of Ohm's law in its very crude form. Just a second. So I proportional to V is the very primary version of Ohm's law, and if we just want to convert this into equation, we get I equals to K into V. And what the scientists found out that this proportionality constant K happens to be exactly equal to the inverse of the resistance of the circuit. That is they found out through experiment, and eventually we can replace this as I equals to 1 by R into V. So we get V equals to IR. So this is the equational expression of Ohm's law. So V equals to IR. Now, one of the key problem that happens that students have to use this equation V equals to IR a lot for the upcoming equation, and this pretty much is the heart and soul of all nearly all the calculation that we're gonna see about after a while. I mean, we're gonna be using this three variable equation a lot. That is very simple. That you, in most cases, you know the resistance value. This should be provided to you in the equation, or you might have to calculate this on a very first few steps of the math. And then depending upon whether you can calculate the voltage easily, you're gonna calculate V first, and then you're gonna immediately find out I, or you're gonna calculate I first, and then you're gonna find out V. So R would be in most cases known to us, and depending upon whether we can easily achieve at V or I, we're going to achieve that variable. And then if we know V, any two of these variables, we can find out the third. That's the very basic way Ohm's law is going to help us. Now, the problem that usually happens, first of all, whenever the equation comes in the exam that write Ohm's law or state Ohm's law, one of the first problem that I've already said, the students forget to write this precondition. You have to write this. Be very careful about this. I'm giving some stars over here. And the second problem that happens, that scientist Ohm said that the current flowing through the conductor is directly proportional to the voltage. He specified that the current is proportional to voltage because what he is trying to propose, that current within a circuit is created because of voltage. This is the output and this is the reason. Let me elaborate what I'm trying to say over here. I mean, why am I telling you this? You have to understand that mathematically V proportional to I and I proportional to V are pretty much the same thing. They both mean the same thing. But in physical terms, there's a difference. Let's say you have a conductor over here. If you keep the conductor as is like this, on its own, naturally, it will not produce a current in itself in such a way that one end is going to become positively charged and the other end is going to become negatively charged. Charges will not automatically produce a voltage difference across an object. Rather, if you have a conductor over here, and if you bring about two oppositely charged ends to its two sides, so that one side is highly positive and the other side is highly negative, or maybe slightly positive and negative, one side is positive, the other side is negative, this conductor is going to produce electron flow across itself in such a way so that it can rebalance the situation. So what I need you to understand, that naturally current flow does not produce voltage difference. It's the other way around. Whenever voltage difference is applied across the conductor, current flow happens to balance out that voltage difference, to make that voltage difference zero. That's the whole idea. So voltage is the cause and current is the effect. Voltage is the independent variable which has to be applied within the situation, and current is the dependent variable which is an outcome of that situation. So that's why scientist Ohm said that current is directly proportional to voltage, not the other one. So be very careful to write it in this manner when in your written statement, that any conductor current flowing to the conductor is directly proportional to the voltage, or PD applies across it. So it's not the other way around. It's not V proportional to I. Why am I telling you this with such emphasis? Because the students use this equation a lot more compared to the amount they actually see or write about this proportionality. So it gets set in their head that V is equals to IR. This is the Ohm's law. And if I just take out the R as a constant out of this equation, if I just remove this out of the equation, I can pretty much write V proportional to I. That pretty much looks pretty logical. So which should mean V proportional to I. Yeah, the equation tells V proportional to I, and V proportional to I is mathematically very much equivalent to I proportional to V. There is not any difference mathematically within these two proportional equations. But scientist Ohm said current is proportional to voltage, not voltage proportional to current, because of the cause and an effect thing. So I want all of you to remember this thing and write your statement with this thing in mind, and so that you do not lose any mark. Any questions so far? No. All right. Now I'm gonna tell you about the two types of combination that we can have. Primarily, we can have series combination, and then we can have parallel combination. What are these things? I'm gonna write one after another. This is one characteristic of series combination, and the other combination is that if I want to write other properties of series combination, same current flow path, so same current. Then I'm going to write sum of all PD equals to applied PD. I'm going to explain what this third bullet means. Second and third bullet. I'm going to explain all three of these bullets after a while. Just let me write down the points so that I don't forget them. Parallel means the first bullet I'm going to write to define this thing is that starting no multiple so this is the definitive points of the series combination and the parallel combination. If I just take one thing at a time, series combination, let me just take the series combination part out. This lasso thing is pretty amazing. Wonderful. What happened? I'll just say it's amazing. Now it's misbehaving. Why? Okay, I just wanted to have some space underneath. Okay, series combination can look like this. Whenever we have multiple components connected one after one like this, let's say I am going to connect one over here, one over here, let's say one that looks like this. Can each of you name these components? What do you call this? This one is named what? This is called
Capacitor, fixed resistor,
yes. This is
variable resistor.
okay. or rheostat. We also call it rheostat. Then
A lamp,
bulb,
bulb, lamp, yes.
bulb,
copper LDR,
This is LDR, light dependent resistor, because of the double arrow coming in. Double arrow means light for electrical symbols. And this one,
thermistor,
this is a thermistor. That is a temperature or thermal resistor is joined together like shondi moto. So we join the thermal resistor, joined together, it becomes thermistor. It is the type of resistor that is dependent upon temperature. So if we make a series combination, this series combination is basically like this. The components will be connected one after another, and there will be no branching over here. There is a single pathway of current. The idea is very simple. If you're gonna send in, let's say, 10 coulomb of charge through this path, you are going to have 10 coulomb of charge coming out on the output side. So this whole thing happens within 1 second, let's say 10 coulomb per second, then you're going to have 10 coulomb per second on the other side as well. So this basically means if you have 10 ampere of current flowing through any part of the circuit, any part of a series combination, you're going to have 10 ampere flowing through every part of this circuit, because there is simply no other way that you can have different value of current. Like I said, that charges are going to get in and charges are going to go out at the same rate, because it's a closed single pathway. So that's the whole idea. Same current flow path, so same current. So every part of the series combination has the same current flowing through it. And then comes the important bit that says sum of all PD equals to applied PD. This is a very important bit. Let me show you this thing. It is very much possible, and it is very much common also, that all the components connected in a series combination might not have the same resistor. Now, if you think about Ohm's law, have a look. Ohm's law gives us what? V equals to IR. Try to understand this equation. Voltage is equal to I into R. We just decided for a series combination that for all the components connected in a series combination, the current is same for everyone. So we can pretty much consider current is same for everyone. And that basically tells us that voltage and R, this should be directly proportional. Because if you take the I as a proportionality constant out of here, V and R should be directly proportional. This basically means that if you have some component that has a higher resistance, it will simply gonna make a higher voltage drop. So V proportional to R. This is applicable for series combination. Try to understand. This is not applicable everywhere. For a series combination, because current flow is a constant, that's why we can write up this equation, or we can convert this equation into this proportionality, that V proportional to R. This means the component that has a higher resistance is going to take more energy to allow that current. The component that has less resistance is going to take less energy. So, and also the sum of all of those energies is going to be exactly equal. So let's say if I just try to give a battery over here, I'm not going to writing this battery value yet. So I'm going to write this battery value a bit later. Let's just say that these components have some different resistor values. Let's say this is 2 ohm. Ohm is the symbol for this is the symbol for resistance unit. Ohm is the unit for resistance, and it has a symbol that looks like this. Is like a horseshoe. uh, this is actually the big omega of Greek alphabet, and the small omega looks like W, but this is the big omega. This is the symbol for resistance, ohm. So let's say this is 2 ohm, this is 4 ohm, let's say this is 3 ohm, let's say this is 10 ohm, and let's say this is 1.5 ohm. So let's say these are the defined resistors that we have. Now, if 10 coulomb or 10 ampere current flows through this branch anyway, we can pretty much calculate what would be the individual voltage drop of all of these components. Because you can see over here, V equals to IR. So if you want to calculate the V, all that you need to have is the value of I and the value of R. You know that the I for all of these components, for each of these components, the I is same. 10 ampere current is flowing through each of them. So the I is known for everyone. All that is different is their resistance value. So this one has a resistance of 2 ohm. So what would be the voltage difference across this component? So if I have a voltmeter over here, what should be this voltmeter reading? Multiply this thing, I into R, what do you get? Current value is 10 ohm, 10 ampere, and resistance is for the first component resistance is 2. So 10 multiplied by 2, you get how much? 20 volt. Is it making sense? I'm applying V equals to IR for this component exclusively. I is 10 ampere because current 10 ampere current is flowing through all of them, each of them, however you say, it's the same thing. And the resistance of this component is 2 ohm, so multiplication gives us 20 volts. And then we have this one should be how much? So this one reads 20 volts. If we have a voltmeter over here, what should be the voltmeter reading for this one? Hold on, Bolo. Help me. Am I muted? No. Yes, Wasima, that's the correct response. This one is supposed to be 40. This one should give us a reading of 40 volt.
40 না
হ্যাঁ তারপরটা
তারপর এটা 30
লাস্টেরটা
1050.
now I did something. uh, I did an intentional mistake, so it's not a mistake actually. Have a good look. This last voltmeter is not connected across the LDR only. It is connected on the two further ends of the LDR and also the thermistor. So how much is the total resistance that lies in between the two connection points of this voltmeter? I mean, between this point, let me use a different color, maybe green. Between this point and this point, what is the total resistance?
স্যার 35 না
Uh,
20
why
প্লাস 15 করে দিছি
this
So
is
it's 15 na 1.5.
this is 10 and this is 1.5.
স্যার এই যে স্যার ইন্ডিভিজুয়ালি করছি স্যার ইন্ডিভিজুয়ালি করে তারপরে প্লাস করে দিছি
So that would be, I think,
35 আসছে
35 আসার কথা না। আমি আবার বলতেছি, এটা হচ্ছে 10 ওহম, এটা হচ্ছে 1.5 ওহম। This is not 1.0 and 1.5. This is 10, this is 1.5. They are widely different.
So volt ki hobe 115.
115 is the correct response. বললাম খেয়াল করো, এই দুইটা জিনিসকে সাম করলে কত হয়? If you add these two up, how much do you get? 10 plus 1.5, how much do you get?
স্যার 11.5
This is the equation. Have a look. Hold on. Voltage drop equals to current into total resistance. So because I have connected the voltmeter over here across both of them, why? I mean, you might wonder, why am I doing this? I want all of you to understand that if you take multiple components within a voltmeter connection on the two ends of the voltmeter connection, the total resistance between the whole voltmeter combination, voltmeter connection should be considered. The total resistance. So in this case, I'm using two components over here, connected one after another. So the total resistance should be used for them, and that should be 10 plus 1.5. So here we're gonna get 115 volt. ঠিক আছে এটা বলবান বুঝে গেছে কিনা দেখো। I is the current, that is 10, and resistance is the sum of these two numbers, 10 ohm from the LDR and 1.5 ohm from the thermistor. So this fourth reading is going to be 115 volt. Now here comes this is the very individual breakdown of the individual voltages, where we had the available of 10 ampere available and other things have working that way. If you add up all of these voltages, how much do we get? 20 plus 40 plus 30 plus 115. So that is 60, 90, 115 means 205. 205 na? Yes. So this battery must be of a source of 205 volt. This is highly impossible. Batteries don't have this kind of high voltages. I mean, it's very dangerous to design batteries of this high voltages, and they are very highly inefficient as well. So this is the idea of the third bullet. Sum of all the PD equals to applied PD, which means if you provide all the potential drops caused by all of the circuits within a series, that should be equal to the total voltage that was provided to begin with. So this, I mean, the reason I'm writing the value of this voltage value last, because I defined the current value first. Because I have already let the current value is 10 ampere, I already said that. That's why I had to go ahead and calculate the individual voltage drops for all of these combination points. And then when I added them all together, I could calculate what is the total voltage across these 2 points. I mean, this is the basic point. Kids, try to understand. Let me draw it with the green. If I have a voltmeter that is connected across these 2 points, and if I have another voltmeter that is connected across these 2 points, so have a look. I'm going around the writing because I don't want to mess up the writing. So if I have a voltmeter connected across these 2 points, you have to understand, I wanted to understand that these 2 voltmeters, this one and this one, they are practically connected across the same electrical point. What I want you to understand that this point and this point are electrically the same point, because there is no resistance in between. So charges are not losing any energy while they are traveling from here to here. This is like the frictionless track that we talked about in our earlier class. So electrically these 2 points are exactly same, and electrically this point and this point, these 2 points are also electrically the same point, because there is no resistance in between these 2 points. There is only a connecting wire. So the reading of this voltmeter reading is 205 volt, and the total reading of this voltmeter reading should also be how much? 205 volt, which is basically the sum of all of these individual voltage drops. Do you understand this part? এই ডিফারেন্ট দুটো ভোল্টমিটারের কানেকশনটা একটু বোঝা গেছে কিনা?
Yes, sir.
আচ্ছা, সো এখানে একটা জিনিস আমি ইনহেরেন্টলি তোমাদেরকে বলে ফেলছি, যেটা অ্যাকচুয়ালি আমি তোমাদেরকে ইকুয়েশন দিয়ে লিখলে ভালো হতো। সেটা হচ্ছে যে whenever we are trying to calculate the combined resistance of a series combination, we simply have to add up the resistances. So for an additional bullet, I can write over here that total combination or total resistance for a series combination can be written as R1 plus R2 plus R3 plus dot, 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 dot. So if you have multiple components connected in series, you just have to add up all of their values to get the total combined resistance of the series combination. That's a very basic idea. So it is also series combination and how you and then we have the parallel combination. So let's give it a try for parallel combination. Parallel combination tells us what? It says multiple branches starting from one point and ending at one point. This to one point actually doesn't mean the same point. I mean, I should have written that ending at another point, but I assume that you have to understand, you should understand the idea of another point by default. So what is the same voltage of PD across all branches? Sum of branch currents equals to total incoming / total outgoing currents. So let me elaborate what this means. Parallel combinations look like this. You have a primary branch that is flowing in from a battery. Maybe let's say I'm going to draw a battery over here, and let's say this is one of your splitting point. So from here, let's say we're going to have one branch. Let's say this is a fixed resistor of 10 ohm. My ohms look so bad. Let's say, did you get see that? Never mind. Let's say this is a variable resistor of, let's say, 15 ohm, and let's say this is a thermistor of 20 ohm. So let's connect them all together. So they have individual current flow path, and they all join up over here once again, and that part gets connected to the battery. এটা হচ্ছে আমাদের একটা প্যারালাল সার্কিটের খুব বেসিক একটা ভিউ. What is happening over here? Current is going to come out from the positive end of the battery, flow in through here, and usually come out over here, and then the current is going to have 3 alternate paths to flow by. So current is going to divide in 3 parts. It's simply going to be split into 3 parts, and how much current is going to flow through how, so in which branch, that's a question of calculation. We're going to see about that after a while. But important thing, because there are 3 available paths, current is going to split 3 ways. So one part is current is going to go through in this way, and the part is going to go this way, and the part is going to go this way. This current flows to 10 ohm, eventually comes down over here. This current flows to the 15 ohm, eventually comes over here. This current flows to 20 ohm and comes over here. So these 3 currents eventually join up over here, and the total current ultimately flows down and gets back to the circuit. The idea is very simple. If you have some current flowing in over here, that same current is going to be split into 3 parts over here, and that same amount of currents are going to get joined up over here or merged over here to produce the exact same current of this value, because the current battery is not going to accept dissimilar values of current. If you have 10 amperes leaving, you're going to have 10 amperes entering. If you have 2.3 amperes leaving, you're going to have 2.3 amperes entering. You are going to have, you have to have the same value of current for any source whatsoever. So that's the idea of this thing. And one more thing, that they also the same voltage or PD across all branches. This is very simple, because you do understand that if I write the voltage of this battery, let's say the EMF of this battery is, let's say, 12 volt. This 12 volt is equally applicable across these 2 points. So let me use a different color, maybe red. So if I now connect a voltmeter, I have to mess up my writing. If I now connect a voltmeter right across these 2 points, this voltmeter reading should be how much? Can you guess? Take a good look. Here's the 12 volt battery positive side. This goes up all the way over here. There's no voltage dropping equipment over here. And here is the negative end of the battery. This goes all the way up over here. There is no voltage dropping equipment over here either. So the battery is defined to have 12 volts. So what should be the voltmeter reading over here? What do you think?
স্যার একই দেখাবে না, আমি জাস্ট
It is going to give us the same
12
value
ভোল্ট
because
দেখাবে না?
yeah, that's the correct response. This voltmeter reading should be 12 volt, and it will be 12 volt. Well, in true case, it will not be 12 volt because of something called the internal resistance, but that's not a part of the syllabus yet, so I'm not going to bother you about this. I'm just telling you on the what can I say, like a whispering note, because this will be introduced to you in your AS level. But for your level, yes, the battery, because there is no voltage drop happening from the positive end of the battery all the way up to this point, and from the negative end of the battery of the up to this point, this voltmeter reading should be exactly the same as the supply. So it means this is going to give us 12 volt. For those of you who are feeling a bit confused about this thing, that why should it be equal, what I want you to understand is that this is exactly what we discussed over here. Have a look. This battery has an individual value of 2005 volt. That's what we calculated. And the total voltage drop across from here to here was also 205 volt. This basically means that the total consumed voltage by these components over here, this 205 volt, was practically supplied from this battery. And electrically, this green point and this green point, they are electrically equivalent, and this point and this point, they are electrically equivalent because there are no voltage dropping agent, or there are no electrical components across these points or across this point, so they have the same voltage value. So this is the same principle that we applied over here, only I did not draw the voltmeter, another voltmeter at that lower side, but this is the principle is very much the same. So in this case, the voltmeter would be 12 volt. Now what I need you to understand, that this 12 volt is equally applicable for this thing, this is applicable for this branch, this is applicable for this branch as well. Having a 12 volt connection means what? I mean, if you now connect a voltmeter over here, what I want you to see, that let's say I'm going to name them, let's say this is voltmeter 1, this is voltmeter so let's say this is voltmeter 2. Do you see any electrical difference between the connection points of voltmeter 1 and 2? I mean, try to understand this thing very minorly, because this can be a point of construction building. What I want you to see, that from here through here, do you have any electrical difference? I mean, are these 2 points electrical equivalent or not?
Yes.
Similarly, these 2 points are also electrically equivalent. Now have a much grander view, and now have a look at the whole thing at a much deeper sense. Let me draw it blue. Let's say this is the positive end of the battery. I want you to see very carefully. Have a look. From the positive end of the battery, this positive end of the battery is practically directly connected to the 10 ohm resistor right over here. And from here, it is directly connected to the negative end of the battery. Have a look. I'm coming through all the connecting wires and the junctions. Connecting wires do not have any resistance whatsoever, which means ultimately we are reaching up over here. Do you now see that this 10 ohm resistor is practically connected directly to the supply? Currents were having some differences. Currents were having some breakdowns. Okay, but the 10 ohm resistor is practically connected directly to the supply. Do you see that? There is a seamless, uninterrupted flow path of charges from the positive end to 10 ohm resistor, and from the output of the 10 ohm resistor all the way to the negative end. There are no obstructions for the in between path. So we can say that the 10 ohm resistor is directly connected to the 12 volt supply because of the kind of electrical connections that we have over here. Is this statement acceptable to you? Polaban. What I can say, I mean, if it doesn't make sense, uh, this is something that can be very easily compared to the uh, কি বলে এটাকে, the plumbing system of a building. Let's say if you have a water tank over here at the rooftop, and here you live in the, let's say, level 1 or level 2, and a long pipe comes down to your level, and then this pipe actually distributes the water outputs in all of your houses in different parts, in your wash basin, in your washroom, in your other taps, in your kitchen, and every other places you have these things. What is the problem here? Okay, so you have all of these individual taps and individual water output level. Have a look, try to understand. If you open up only one of these, water is going to flow, come down through this junction point, and immediately flow over here. If you open up another one, water is going to flow more through the same pipe and immediately flow through here. This pipe is thick enough to be able to provide uniform water flow for all of your outlets, or ideally they are supposed to be so. You have to understand this thing as well. Even if we allow multiple of these components to allow current flow directly or continuously, these wires, which are considered to be of zero resistance wires, have the capability to withstand slash to accept infinite value of current. I mean, 10 ampere, 12 ampere, 100 ampere, 2000 ampere, 2 million ampere, doesn't matter. A theoretical wire that is a connecting wire is capable to carry any value of current, which means if this branch carries some current, if this branch carries some current, if this branch carries some current, if you sum up all of these currents, that total current will be coming out through here when all three of these branches are working together. They are working simultaneously. এই পার্টটাকে বুঝতে হবে। And also the pressure of the EMF across applied across all of these components would be exactly same as the supply voltage. In the same way that the pressure at any of the water outlets should be the difference from the pressure water height level of the water tank all the way to your faucet level. I mean, if this is your H, then the pressure that you're going to get at this point is going to be delta H rho G. So if you are at a much lower level of your building, your faucet is going to have more force of water. You're going to have a higher kinetic energy coming out. If you are pretty close to the tap, for example, if you are living on the top floor, you're not going to have that much pressure. So that's the very basic idea, that you are going to have same amount of EMF at every single part of your parallel branch. However, the current flowing through individual branch can be different. এই আইডিয়াটা মানে ধরা গেছে কিনা যে ইএমএফ কেন ইকুয়াল হবে, because they are all being connected to the supply individually, or they all have the same amount of push from the supply to flow charge through themselves. Does it make sense? I hope it does. So if we now want to calculate the current flow through these individual branches, I'm going to go ahead and do that. The current flow through this branch should be how much? We are going to use the formula V equals to IR, Ohm's law, and in this case we are trying to calculate current, so this is going to be V by R. Now the V is a constant for all of our branches over here. So here the V is 12 volt. The only thing that is going to be variable is the value of resistance, so I'm going to assume the resistance is the box. So in this case 12 divided by 10, this gives me 1.2 ampere. In this case 12 divided by 15, so what should be this value? 12 by 15 করলে কত হয় ক্যালকুলেটর? 0.8 ampere, and this branch is 12 by 20, 0.6 amperes. So these are the individual branch currents. So if we just now sum all of these currents all together, we can calculate the total incoming current or the total outgoing current, which is going to be 2.6 ampere. এই পর্যন্ত কি বুঝা গেছে বলাবান? ক্যালকুলেশনের প্রসিডিউর এই পর্যন্ত বুঝা গেছে কিনা?
Yes, sir.
Yes, sir.
আচ্ছা, another thing that I would like to also show you is that how do we get the formula for the parallel combination thing? I mean, how does it even come into existence? Here's the idea. Let me show you. If I just name these resistors as, let's say, R1, let me use maybe black. Say this is R1, this is R2, this is R3, and what the current values are I1, this one is I2, and this one is I3. And let's say the total current is only I, and the supply value voltage is, this is our capital V. And the voltmeter reading, and the voltage across this one is V1, voltage across this is V2, this is across V3. So if we now try to develop some equation over here, have a look. I'll keep the circuit in view. Okay. What we have seen that the V1 equals to I1 R1, V2 equals to I2 R2, and V3 equals to I3 R3. Each of these three things is very much similar, equal to because V goes to V1, V goes to V2, and V goes to V3. This is true. However, so if from this equation we subject the I1 can be written as V1 by R1, I2 can be written as V2 by R2, and I3 can be written as V3 by R3. Now, if you consider the current value, have a look at this junction point. I current comes in, gets split into three parts, I1 plus I2 plus I3. And now I can replace all of these individual values of the I1, I2, I3. But how about I, which I'm going to do in the next step? That how about I? Now comes the basic idea that what do we understand by an equivalent resistance? An equivalent resistance is basically, the idea is that if all the components that we're considering for a certain part of a circuit or for the whole circuit maybe, if all of those resistors are replaced by a single value resistance, if the combination of all the resistors is replaced by a single value resistance such that the current flow remains the same, then that value resistor is called the equivalent resistance of the whole combination. আইডিয়াটা খুব সিম্পল। মনে করা হচ্ছে এখানে আমাদের তিনটা ব্রাঞ্চের ভেতর দিয়ে, let's say within these three branches we had individual currents of 1.2 ampere, 0.8 ampere, and 0.6 ampere. The total current was 2.6 ampere. Other than having this whole three branch combination shebang, if we replace this whole thing and could place one single value resistor across these 2 points such that this current value would remain same, then that single value resistance would be called the equivalent resistor of this whole combination. So do you understand the idea of equivalent resistance? It's a replacement, it's a single value replacement. So let's say if we now assume that, I'm going to draw the circuit over here once again so that you can make sense out of it. So let's say this is the battery of 12 volt, and let's say this is our equivalent resistance. I'm naming this RP because the combination of the this is the equivalent resistance for a parallel combination, and this is the whole combination over here. So and let's say in this case also the current is going to be still 2.6 ampere. That's the whole point of the equivalent resistance. The current value should be same all over. So in this case, if we consider this current is I and this was our supply voltage V, then I can very much write from this circuit, I can write that V equals to I into RP, or I can write I equals to V divided by RP. Does this equation make sense with you? The idea of equivalent resistance. এটা কি বুঝা গেছে?
Yes, sir.
ঠিক আছে। So এখানে যদি আমি এখন আস্তে আস্তে রিপ্লেস করি, so I can replace this thing I as V divided by RP, and this I can replace as V1 by R1 plus V2 by R2 plus V3 by R3. But interestingly, V1, V2, V3, they are all the same, which means I can pretty much divide both sides by V. So just to help you understand the math a bit better, I'm going to replace all of them by V. And we can cut off the whole equation on both sides. So we get this expression, 1 by RP equals to 1 by R1 plus 1 by R2 plus 1 by R3. This is practically the ultimate equation for the common resistance of a parallel circuit. I'm going to write this in clear over here. If we have multiple combination, multiple resistors in current in parallel, 1 upon combined resistance is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, and you can go on like that. You have to understand this thing very clearly. These R1, R2, and R3 are the individual branch resistances. It's important. R1, R2, and R3 are the individual branch resistances. Now you might wonder, what does that even mean? Uh, I'll explain that this sentence with a bit more elaborate example just after a while. But what I want you to understand one thing is that this is the most common expression that you're gonna find in your books, and this is the perfect equation. This is symmetrical on both sides, looks good. But I personally don't like this expression. There is a there is a different expression of the same equation that I personally like. That expression looks like this. Have a look. Can someone tell me the difference between these two equations? Do you understand what I just did? I wrote
Yes, sir.
this whole thing within a bracket, and then I gave the minus one over here, over here. Now, why do I like this expression more? Why do I like this one more and I like this one less? Because of one thing. Should I would say, whenever the kids are trying to calculate the combined resistance or the equivalent resistance of a parallel combination in their exams, in many cases, they do this part. They do the 1 by R1 plus 1 by R2 plus 1 by R3. And then they do, okay, they might have done this for quite a good number of components. But what is important, this sum is not the combined resistance of the parallel combination. This is inverse of the common resistance of the parallel combination. To get the parallel combination, you have to once again invert it. So whatever the sum that you get, 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus 1 by R5, blah, 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 you get the whole sum. Then you have to inverse it. And only then do you get the actual RP value. In many cases, not in most, in all cases, in many cases, students forget to do that last reversal. And they write that exact value on their answer and eventually lose mark. Whereas this expression, on the other hand, is far too easier to mess up. It is far too easier to mess up because for one thing, you're going to start your equation with a bracket. So if you do not finish your bracket at the end, your calculator is going to give you a syntax error. So you have a built-in checking system. And if you forget this error, if your calculator gives you syntax, so then you can remember, oh, I have to give the bracket closed because I have to provide another minus one over here. And in your calculators, you have a x to the power minus one button built up automatically. It is beside the x cube button and above the log button. Do you see that? X to the power minus one on the black buttons in your calculator. Do you see it?
Yes.
Okay, so it's easier for you to write numerical values in this format. So if you have a combination like this, for example, let's say if you are trying to calculate the parallel combination of this circuit over here, by the conventional formula, what you should do, you should write, you have to use the fraction sign. There's a fraction sign, right, in your calculator. Do you know there's a fraction sign in your calculator? AB by C, that one. So you have to write this thing in that format, and eventually you have to do the inverse. Other than that, what you can do, you start with a bracket, and then you write 10 x to the power minus 1 plus 15 x to the power minus 1 plus what, 20 x to the power minus 1. Now, if I do not close it with the bracket, give an equals to, I still get a value, but that is not my final answer. Sorry, there was supposed to be a syntax error. Why don't I get the syntax error? I think there is just a bit of a mistake. I'm supposed to get a syntax error. Anyway, the final is, I'm not getting a syntax error. I'm going to look into the syntax error later. But what I'm trying to tell you is that having this format is far too easier to write on the calculator and not to mess up, because the final to the power minus 1 is automatically built in. So I personally like this format paper better, but this is just a perfectly personal preference. If you like this format better, if this looks more symmetric to you, be my guest, no problem. My honest request is that don't mess up the calculation. Do not forget to do the last inversion if you are using this expression. And if you're using this one, do not forget to put the last to the power minus 1 over here. So for this whole combination, we can calculate that the total parallel combination is calculated to be 4.6153. So I'm going to write 4.62 ohms. And that pretty much makes sense with our voltage as well, because if I now do calculate the voltage. If you do multiply this with 2.6, you're gonna get nearly 12 volt. You're not going to get exactly 12 volt. Have a look. If I now calculate the voltage drop across these 2 points, like let's say V equals to IR. So if I use 2.6 multiplied by 4.62, you're not gonna get exactly 12. How much did you get? You get 12.012 volt. Now, where did this extra 0.012 volt come from? This extra 0.012 volt comes from rounding off error. And this is a very common type of error that can happen in electricity calculations. This is why in electricity calculation, I always recommend the students to maintain up to 4 decimal places for your working values. Only when you're writing your answer on the dot 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 space, you write the 3SF answer. But for all of your working numbers, you prefer to carry 3 up to 4, at least 4. I mean, up to I prefer to carry, I personally prefer to carry 4 decimal places number for in between values, which means that if I have to use one of the calculated number for a later calculation, I prefer to use that number up to 4 decimal places, not the 3SF rounded form, because rounding off error can prove to be pretty huge whenever you are doing it multiple times. Try to understand. Let's say this number was actually 4.615 something something. I made it 4.62, which means I am adding 0.05 to this number. Now, if I multiply this number for some calculation by 5, I'm actually making that mistake 5 folds. If I multiply this number by 500, I'm practically making that mistake 500 times fold. So whenever you are doing rounding off for your within your math, you're actually introducing a potential error, huge amount of potential error, unless you're very careful about it. Whereas if I did keep it for a much bigger number of decimal places, that error amount would have been for a much smaller fraction of the number, because it will be in the further right side on the decimal side of the decimal point. So that's the important bit. That's how I prefer to do the calculation, to have less and less amount of rounding of error. But you can develop your own method if you want. But I'm telling you what I personally like, and I also want the students to adopt this as well, to understand the importance that this is how it works, and this is why it works that way. That we should not have round of error, because at the end of the day, we will see that whenever it will be start to solve the large circuits, to have a much better and holistic understanding of how the circuit works, and also the mixed combination of series and parallel combinations, you'll see that if we do not carry up to 3 or 4 decimal places for the in between values, the final answer can be quite different for even for within the 3SF range. I mean, let's say I have kept my numbers up to 4 decimal places, and let's say another person have not kept their values to 404 decimal places. It is possible that some of the calculated numbers within their 3SF values would be significantly different between mine and that other person. So that is something that we all want to avoid, because the mark schemes are not going to have alternative values for numerical answers. In the mark schemes typically has one value, and I want all of you to have the correct value. So precision actually is an important thing. So that's pretty much it for the parallel combination. In our next class, we're going to see about the combined calculation, and I would like to propose one. আচ্ছা থিওরি ক্লাস এখানে শেষ, আমি একটু টাইমিং নিয়ে আলাপ করতেছি, আমরা রেকর্ডিংটা